students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as surface tension. Yesterday we'd seen capillarity. Let's see what is capillary action. What do we understand by capillary action? Now, first of all, what is a capillary? A tube which has a very small bore is called as capillary. What is a capillary? A tube having a very small bore is called capillary tube. Fine. Now let's see how does the capillary action work. Suppose if I have a beaker filled with water, and let's assume that I insert a capillary tube in this. Right, so there will be a meniscus that will be formed here. There will be a meniscus that will be formed here. Similarly, inside also you will have a meniscus formed. Now, inside the tube, what will happen is that the level of water will rise. Right, the level of water will rise. The smaller the bore, the more will be the rise in the level of water. Now, if I were to do the same experiment with mercury, in the case of mercury, the level of water would drop, right? This particular action is called as capillary action, right? So what is capillary action? If a capillary tube is held with its one end dipped in water, dipped in water, it is observed that the water level in the capillary, the water level in the capillary tube, water level rises in the capillary tube. Fine. And this is called as the water level rises in the capillary tube, and the water level inside the capillary tube is higher. The water level inside the capillary tube is higher than the level outside the tube. Right? Question. Now, before this is if it is water. On the other hand, if I do the same experiment with mercury, I'll say that if the capillary tube is held with one end dipped in mercury, if a capillary tube is held with its one end dipped in mercury, then it is observed that the mercury level falls in the capillary tube. The mercury level falls in the capillary tube. The mercury level the mercury level inside the capillary tube is lower than the level outside. Right? So this is called as, now this rise and fall in the level of the liquid inside the capillary tube is called as capillary action. That means if the capillary tube is dipped in a liquid which wets the capillary tube, then the level of the liquid will rise in the capillary tube. On the other hand, if the capillary tube is dipped in a liquid which does not wet the capillary tube, then the level of liquid in the capillary tube falls. And this phenomena of rise and fall in the liquid level inside the capillary tube is called as capillary action. Right? So I can say thus, if the capillary tube is dipped in a liquid which wholly or partially wets the capillary tube, which wholly or partially wets the capillary tube, the liquid level rises in the capillary tube. The liquid level rises in the capillary tube. On the other hand, if the capillary tube is dipped in a liquid which does not wet the capillary tube, the liquid level falls in the capillary tube. Thus, what is capillary action? Therefore, I can say what is capillary action. Capillary action is defined as the phenomena of rise and fall. The phenomena of rise and fall of a liquid inside the capillary tube. Right? So that is what is called as capillary action. Why do we get this? Question: why does capillary action take place? Explain capillary action. Right? Now, in order to explain capillary action, let us understand. Let's draw this diagram. Capillary tube immersed in a liquid that wets the liquid. Which wets the capillary tube. Since the liquid wets the capillary tube, the level of liquid in the capillary tube will rise. Let us consider initially that the level of, why does it rise? Let's try to find out. Right? Let's assume that all of them are at the same level. Consider 4 points here. One just outside the capillary tube, one just inside the capillary tube, one just outside the liquid surface, and one just inside the liquid surface. So I'm going to consider 4 points to explain to you why the level of water will rise in the capillary tube. So we'll say that consider a capillary tube immersed in a liquid which wets the tube, right? Which wets the tube. Now, as soon as the capillary tube is immersed inside the water level in the capillary tube will rise to a definite height. Now, before that, let us consider a situation. Consider a situation before the movement of water inside the capillary tube. Now, due to the angle of contact phenomena, the shape of the surface of water inside the capillary tube is going to be concave. We done the angle of contact phenomena. Due to the angle of contact phenomena, the shape of the liquid inside the capillary tube will be concave, right? Now consider, let A, B, C, D be 4 points or be points such that A is just above the curved surface inside the capillary tube, is just above the curved surface, inside the capillary. B is just below the curved surface inside the capillary, just below the curved surface in the capillary. C is just above the plane surface outside the capillary, is just above the plane surface outside the capillary, and D is just below the plane surface outside the capillary. So I am considering 4 points. Now let us assume that PA, PB, PC and PD be the pressures at these points. Let PA, PB, PC and PD be the pressure at A, B, C and D. Right? Now, we know that the pressure in the concave, we know that the pressure on the concave side of the liquid is greater than the pressure on the convex side. That is the reason why you have a concave side. We've learned this from angle of contact phenomena, I can say. But the pressure on the concave side, of the liquid is always greater than the pressure on the convex side, The pressure on the concave side is greater than the pressure on convex side. That means, guys, if you see the diagram, the pressure here on the concave side should be greater than the pressure here on the convex side. Therefore, I can say that PA is going to be greater than PB, right? Now, if I consider outside the capillary tube, you have a plane surface. Since you have a plane surface, that means the pressure on both sides of the plane surface should be equal. The pressure is same. Pressure is same on both sides of the plane surface. That means I can say that PC is equal to PD. But we know, guys, see this, PC is equal to PD. Right? Right. PC is equal to PD. But we know that PA and PC, from where did this pressure come? This is nothing but the atmospheric pressure. That means PA should be equal to PC should be equal to atmospheric pressure. Both of them are nothing but atmospheric pressure. But I can say that PA is equal to PC is equal to atmospheric pressure. Right? That means I can substitute the value of PA as PC in this equation. So in that case, I'll get PC is greater than PB. Right? PA is equal to PC is equal to atmospheric pressure. Therefore, I'll get, in that case I can say that since these two are equal, that means if both the left hand sides are equal, that means I can say that PD is greater than PB. If both these left hand sides are equal, guys, that means I can say that PD has to be greater than PB, right? That means instead of PA I can write PC, instead of PC I can write PD. So I'll get PD is greater than PB, right? That means now PD and PB are both are points inside the liquid. That means the pressure at a point below the plane surface is greater than the pressure at a point below the concave surface, right? That means I can say that therefore, even though points B and D are at same horizontal level, points B and D are at same horizontal level inside the liquid, the pressure at point B is greater than pressure at point B. Hence, the liquid cannot remain at equilibrium. Hence, the liquid cannot remain at equilibrium. The liquid cannot remain at equilibrium and starts flowing into the capillary tube. Into the capillary tube. Right? It starts flowing into the capillary tube and rises above the point B and rises above till the pressure at point B, till the pressure at point B becomes equal to the pressure at point D. Right? And this is the reason why the liquid rises in a capillary tube. Therefore, liquid rises in the capillary tube. Right? That's how we can prove that, because to make the pressure at equilibrium inside the liquid, the level of liquid has to rise inside the capillary tube. Next, let's try to find out a mathematical formula for surface tension. Expression for surface tension. Now consider a capillary tube of radius r. Consider a capillary tube of radius r dipped vertically in water. Right? Now due to surface tension of the water level rises inside the capillary tube. Due to the surface tension of water, the water level rises inside the capillary tube. Rises inside the capillary tube. Let's try to find out what are the forces inside the capillary tube. Let's draw a capillary tube and let's try to find out the forces inside the capillary tube. Beaker, capillary tube, level of water, level of water rises inside the capillary tube. This is the level of water inside the beaker. Let's assume that the level of water rises to a height h above the surface of the liquid, right? So let's assume that this height is h. H is the height to which the level of water rises above the plane surface. Right? Let's assume that inside the capillary tube there are going to be 2 points of contact, point A and point B. Fine? Now, let's try to find out the forces or at point A and at point B. Right? First of all, I can say that let H be the height. This is your capillary tube. Let H be the height of water inside the capillary tube. Inside the capillary tube. Right? In which case I can say inside the capillary tube above the free surface. Right? So in which case I can say that the meniscus is going to be concave. R is the radius of the capillary tube, which we have already said, and let's assume that point A and B, at points A and B, that's a point of contact. At points A and B, I can say that the forces of surface tension, the forces of surface tension, the forces of surface tension, T will always act tangentially, to the surface. Right, surface tension will always act in tangential direction to the surface with the walls at the point of contact. With the walls of the capillary. Okay, now I'm going to just show you point A here. This is your point A, which was inside the capillary tube. Now let's try to find out what are the forces that are going to be acting on it. Now the surface tension T is going to be your force per unit length. That's how you define surface tension. Now, why is there a surface tension at point A? There is going to be surface tension at point A because of multiple forces. One, the force of adhesion between the glass tube and the liquid. There is going to be some force of attraction between the glass tube and the liquid, and next the force of cohesion between liquid molecules. As a result, the glass molecules at A and B will attract the molecules with a force per unit length T in the direction of, say, AP. Right? This is the direction in which the glass molecules are going to attract. This is the direction in which the glass molecules are going to attract the liquid molecule. That's the reason why you have a concave structure, right? So I can say that the force of surface tension T is the force per unit length From where does it arise? Right? Now it refers to the force experienced by a molecule at A. It refers to a force experienced by a molecule at A due to 1. The force of adhesion between the glass molecules due to the glass molecules, and second, the force of cohesion due to the liquid molecules. Right, two forces acting at point A. One, the force of adhesion due to the glass molecules. Second, the force of cohesion due to the liquid molecules. As a result, the molecule at A attracts, or as a result, the glass molecule at A attracts the liquid molecule with a force per unit length T, in the direction of AP. Since it is attracting, guys, can you see this? Since it is attracting the water molecule in the direction of AP, so since this is a force, it can be resolved into two components, one along horizontal and one along vertical. This force can be resolved into two components, one along horizontal and one along vertical. Now if this is the angle that it makes with the vertical, then in that case this is going to be equal to T sin theta, and this force is going to be T cos theta. Now T sin theta is going to act along the circumference. There are so many molecules along the circumference which are going to try to pull the water molecule outside. Hence, the net force that will act along the circumference will become 0. Guys, if I show you the top view of the liquid, this is my top view of the liquid. If I see from above the capillary tube, you would have T sine theta here, T sine theta here, T sine theta in all directions along the circumference. Since you have T sine theta in all directions along the circumference, what will be the net force along the circumference? 0. That means the only force now that will act will be the T cos theta force, which will be in upward direction. T sine theta, which is along the circumference, is going to cancel each other, because you would have forces acting at different point in opposite directions, right? So I can say that resolving the force per unit length T, resolving the force per unit length T, I can say that we get T cos theta acting vertically upwards and T sine theta acting in horizontal direction. Now I can say the horizontal component due to all molecules along the circumference, the horizontal component due to all molecules along circumference cancel each other. Hence, it is only the vertical component that remains effective. I can say only the vertical component is effective. If only the vertical component is effective. Now, the meniscus touches the walls of the tube along the length 2 pi r. The meniscus touches the walls of the capillary tube the meniscus touches the walls of the capillary tube along the length. Now the length of the capillary tube obviously is going to be the circumference 2 pi r. Therefore, I can say that we know that force per unit length is nothing but T cos theta. That is going to be my force per unit length. Circumference of the capillary tube is 2 pi r. That means what will be the total force that will act in upward direction at every point? The force acting at upward direction is T cos theta and the total length is 2 pi r. Hence I can say that the total upward force is going to be T cos theta into 2 pi r. Right? Do we understand this? At point A, the upward force is T cos theta. The total number of points are, the total length is 2 pi r. So that means the total upward force will be the force at one point multiplied by all the length of all the points. Now this upward, if there is an upward force, this has to be balanced by a downward force. What is going to provide the downward force? The weight of water which is acting in downward direction, right? For which first let us find out the volume of the water in the meniscus. The volume of water in meniscus is going to be, now the volume of water in meniscus. How is the meniscus, guys? Suppose if this is your capillary tube, if I take a section of the capillary tube, this is how the meniscus is going to be, right? So the meniscus is going to be pi r square minus pi r square minus pi r square is the volume I want into r minus 2 by 3 pi r cube. Question: how? Right now, the meniscus can be considered spherical in shape. Hence, the volume of the liquid in the meniscus is going to be the difference between the volume of the cylinder. This is your cylinder. I'm assuming this to be a cylinder, right? So, volume of the cylinder is nothing but pi r square into the height. I'm assuming the height to be h, and I'm assuming, so this is your cylinder minus the volume of the semisphere. The volume of the liquid in the meniscus, this is your liquid in the meniscus. The volume of the liquid in the meniscus can be considered as the difference between the volume of the cylinder of radius r and length r and the hemisphere of radius r. Right? That's how I got that formula. So hence I can say that this is going to be nothing but pi r cube minus 2 by 3 pi r cube common. So this is going to be 1 minus 2 by 3, 3 minus 2 by 3, that's pi r cube by 3. Right? This is the volume of the liquid in the meniscus. Besides that, how much is the volume of the total volume of the liquid in the liquid column? The volume of liquid in liquid column. See, the liquid column is made up of meniscus plus the level above the plane surface. So you have water here. Now this is nothing but it is a cylinder where the radius is r and the height is h. Right? The height is going to be, see, the total height is h from here to here. And this height you have considered as r. So the height of the liquid is going to be nothing but, we always consider the height up till lower meniscus. So in that case you will have volume of the liquid in the liquid column is pi r square h. This is going to be my pi r square h, the cylinder, plus the liquid in the meniscus, that's pi r cube by 3. That is going to be my volume of the liquid in the liquid column. Here I could take pi r square common. So this is going to be h plus pi is gone, so r by 3. This is the total volume of the liquid in the liquid column. Now let us assume that rho is the density of the liquid. Let rho be density of liquid. If rho is density of liquid, now we know that density is mass. Density is nothing but mass upon volume. Therefore, I can say mass is density into volume. Now, what is the weight of the liquid? Weight of the liquid is going to be mg. M we found out is rho vg. Rho v you found out is pi r square h plus r by 3 into g. This is the weight of the liquid. Weight of the liquid is going to act downwards, and you also have an upward force. Now since the liquid is at equilibrium inside the capillary tube, for equilibrium of liquid in the tube, the upward force should be equal to the downward force. The upward force you had found out was T cos theta into 2 pi r. Downward force you found out is rho pi r square h plus r by 3 into g. Pi and pi gets cancelled, r and square gets cancelled. Therefore, T is going to be equal to rho r h plus r by 3 g upon cos theta. That is going to be the surface tension that is going to act on the liquid. Now, if the angle of contact is 0, if angle of contact is 0, then cos theta will be equal to 1 because cos of 0 is 1. So in that case, I missed something, 2 cos theta. Right, in which case I'll get P is equal to rho r h plus r by 3 g upon 2. This is going to be the tension if the angle of contact is 0. Now if the weight of the liquid in the meniscus is neglected, if weight of liquid in meniscus is neglected, weight of liquid in meniscus is neglected, that means the volume of the liquid in the liquid column will be just pi r square h. So in that case, T will be nothing but rho r will be nothing but, wait, we'll just do this again. Then the upward force will be T cos theta 2 pi r. The downward force will be density, only the liquid in the column, so that's pi r square h into g. Pi and pi gets cancelled, r and r gets cancelled, so then the tension would be rho r h g upon 2 cos theta. Right? If theta is 0, that means if the angle of contact is 0, then T will be equal to rho r h g upon 2. Now if T is equal to rho r h g upon 2, then I can say that h is going to be nothing but 2T upon rho r g. That will be the height of the liquid in the capillary tube, right? And with cos theta, if I write, I can say, or I can say h is equal to 2T cos theta, 2T cos theta upon rho r g. That will be the height of the liquid inside the capillary tube, right? Now, what are the factors that affect the height of the liquid inside the capillary tube? First, impurities. This was third. Fourth, effect of impurities on the height of liquid inside the capillary tube. Right? Now, surface tension is very sensitive to impurities. Even a very small contamination of the surface can cause a large change in the angle of contact, and consequently the surface tension changes. Fine. So if organic substances are dissolved in water, the surface tension decreases. I can say that surface tension is very sensitive to impurities. A small contamination of the surface can cause a large change in the angle of contact and surface tension Now let's see what are the different types of impurities you can have. Now if you have organic substances dissolved in water, the surface tension of water will decrease, right? This is because the intermolecular forces of attraction due to the organic substances which are the intermolecular forces of attraction decrease due to the organic substances which are carbonic compounds, right? If organic substances are added to water, then surface tension decreases. Why? Because the intermolecular forces decrease, because the intermolecular forces decrease due to organic substances carbonic compounds. Right? So, in general, when impurities are added to water, in general, if the impurity added to water is less soluble, then the surface tension of water decreases. So, the general rule is impurity added to water is less soluble then surface tension decreases. Less soluble than surface tension decreases. Right? However, if you have inorganic compounds dissolved in water, then the surface tension increases because of the presence of ionic compounds. There you have carbonic compounds, that is, you have covalent bonds which are not very strong, whereas in the case of inorganic substances, you have electrovalent bonds which are very strong, being polar in nature. Right? So, if inorganic substances are added to water, then surface tension increases. Why? Because intermolecular forces increase due to the presence of ionic bonds. There you have covalent bonds which are not very strong. Here you have ionic bonds which are very strong, and that cause the surface tension to increase. So in general, impurities added to water which are highly soluble. If the impurity is highly soluble, then it will increase the surface tension. So I can say impurity added to water is highly soluble, then surface tension increases. So if it is less soluble, then the surface tension decreases. If it is highly soluble, then the surface tension increases. The second factor that affects surface tension is effect of temperature. That's the other factor that affects surface tension. As the temperature changes, surface tension also changes. The variation of surface tension with temperature can be given by the formula as temperature changes, surface tension also changes. The changes in surface tension due to variation of temperature can be given by the formula T m Vx raised to 3 by 2 is equal to K theta 0 minus theta minus D. Right? Where theta is the critical temperature, That is, it's the boiling point. Critical temperature means that's the boiling point. X is the coefficient of association of liquid. X is coefficient of association of liquid. How much will be the cohesive force, right? Theta is the temperature at which the liquid is, and D is a constant. The value of D varies between 6 to 8. M is the molecular weight. And V is the volume of the liquid. V is the volume of the liquid, and K is again a constant. What else is remaining? T. T is the surface tension.
Theta 0.
Theta 0 is your critical temperature. Theta 0 is the critical temperature. Critical temperature means the boiling point. X is your coefficient of association. How much is the cohesive force? Theta is the temperature at which the liquid is, right? D and K are constant. M is the molecular weight. V is the volume, and P is the surface tension. By using this formula, you will come to know how much will be the change in surface tension for a change in temperature. Fine, do we get this thing clear? Generally, as the temperature increases, the surface tension decreases. Temperature and surface tension are inversely proportional to each other. Right? This finishes the theory of this chapter. We'll stop this here for the day. Thank you very much.